Welcome back. Today I'm going to be completing part C of homework 3 for separations. What we're going to be doing today is we're going to derive the Fency equation. And to get started in our derivation, we're going to need to draw a simple XY diagram with an equilibrium curve. So we've got our 45-degree angle. We've got our equilibrium curve. We're going to consider our X, our liquid composition at our reboiler, which we're going to call XR. Now we know as we take steps up from the reboiler, we've usually been saying that N is at the bottom and you count down to the top, and the top, the condenser, is essentially stage 0. So as we take a step over, we get our liquid composition at Xn. As we take a step up and over, we get our composition Xn minus 1. And as we continue to take those steps further and farther up, we eventually get to our X1, being our stage right below our condenser. We can also consider that we know that if the liquid composition at the reboiler is XR, then the vapor composition is going to be YR. And going on from there, we can consider in a typical distillation column, we're going to have a light key and a heavy key. So we can say from previous derivations that our YLK is our vapor composition at R for light key is going to equal our YHK not YHK is going to equal our K for our LK, our partition coefficient, times our XLK. And these are both at the reboiler. And we'll recall that our partition coefficient K is going to equal our Y value over our X value for a given mixture. We can also say that the Y for our heavy key at our reboiler is going to equal our K for our heavy key times our X for our heavy key at our reboiler. Now, if we divide these two expressions out, what we get is that our YLK over YHK, or Y for our light key and our heavy key at our reboiler, is going to equal alpha. So we would call alpha is the ratio between two of these K constants, times our X, light key, our reboiler, move this R outside these parentheses, over our X for our heavy key, all at our reboiler. Now we can also consider that our YR remains constant between our XR and our XN, that is, our vapor composition doesn't change when moving between these two. So we can also say that our XLK over XHK at N is going to equal alpha times our XLK over our XHK at R. And if we sub this expression into our next Y value, our YN, we get that our YLK over YHK at N is going to equal alpha squared times our X reboiler. And if we continue this trend downward, we can also see that yn doesn't change between xn and xn minus 1, so we can say that xlk over xhk at n minus 1 equals alpha squared times xlk over xhk at r. And we can go so on and so forth, moving up to our yn minus 1, putting in another alpha cubed, until we begin to notice a trend here. And that trend is that eventually our xlk over xhk at our distillate must eventually equal alpha to the n, with n of course being our number of stages, times xlk over xhk at the bottoms. Once we erase all of our derivation work here, we can solve this expression for our n, our number of stages, to get our Fensky expression, which tells us how many stages we need for these given compositions. So I'm going to move this over to here so we get a little more room to work. For xlk over xhk, our distillate equals alpha n times xlk over xhk for bottoms. Cool. So obviously our first step here is going to be to try to isolate this n. So we're going to divide this over to here, which is going to give us xlk over xhk at the distillate over xlk over xhk at the bottoms is going to equal alpha to the n. And then, of course, we're just going to need to take the log to isolate our n value. What we end up getting is that n, the number of stages, equals the log of our xlk over xhk at the distillate divided by the log of our alpha value times the log of our x at lk over x at hk at the bottoms. And this expression right here is our Fensky equation for our number of stages. So moving on to the next part of part C, we're going to derive the Underwood equation, which goes hand in hand with the Fensky equation here. So let's go ahead and move on and derive that. All right, moving on, we are going to go ahead and derive the Underwood equation. So getting started in deriving the Underwood equation, we're going to look at like the rectifying section of a distillation column. So starting this out similar to how I did before, just going to draw out our XY diagram. But this time I'm going to put a rectifying line on there. A little R over R plus 1. We're going to remember that as we're going along our equilibrium curve, taking our steps over our operating line downwards, we've reached this point where as we're adding more stages, our compositions are not changing, and this is what's called the pinch point. And considering that pinch point, we will know that yn equals k xn and yn plus 1 equals k xm plus 1. But we know that when approaching this pinch point, and we look at these values, they're essentially the same. Both of these are essentially the same. At our pinch point. As once you get, like I said, once we come down to this pinch point, for each stage, our compositions aren't really changing anymore. Now this is relevant for the next part of the problem, but to move on here, we're going to take a look at the general material balance for the rectifying section, which we'll recall is our YIV equals our XID times D, and we're just saying I because we're considering this is probably a multi-component system, so I is whichever component we're considering, plus XI times L. We're also, what we're going to remember is that our XI actually equals L over Ki, as we've discussed many times before from just the general definition of K. So if we plug that into our equation, we get that YIV equals XI D times D plus L L over K here, that's incorrect. I was confused. YI over K. So XID plus YI over AI times L. And then if we go ahead and we isolate our YI and our XI, we know that YI times V minus L over KI is going to equal our XID times our D. And then moving on from here, we're going to isolate our YI completely. So we're going to say YI equals XID times D over V minus over AI. At this point, we're getting very close to what we would call our Underwood equation, where we need to move a couple things around to get to the actual form that we're going to need here. So the first thing we're going to do, kind of counterintuitively, we're going to multiply by Ki over Ki, which is going to give us Yi equals XID times Ki times D over V times Ki minus L. And what we're also going to do to get this into the form with alpha, we're going to multiply each by 1 over Kr, Kr being the K value for another component in the system, possibly if we're considering I and R to be the heavy key and the light key. So an example that might be, but to multiply by 1 over Kr, the K for another component in our system, or 1 over Kr over 1 over Kr, which will give us that Yi equals alpha XID times D over, and this is alpha just going to stick with alpha for the remainder of this explanation. Over v times alpha minus L over K R. Another pretty weird and unintuitive thing that we do to derive this Underwood equation is we're going to pull out this v from the denominator here. And what that's going to result in is that we're going to say that, again, yiv is going to equal alpha xi d times d over alpha minus L over D times KR. This is where Underwood really comes in. The guy decided that this value here, L over D times KR, is this phi constant. So he subbed that in to this equation as well, giving us yiv equals alpha xi d times d over alpha minus our phi value. And then we'll remember that our summation of y goes to 1. Meaning that we can essentially just eliminate this yi here, we just get our v, and then we can sum our other side, leading to our overall equation that v equals our distillate flow times the sum of alpha xi d over alpha minus that phi value we were talking about. And that right there is our Underwood equation. Now that we've got our Underwood expression for the rectifying section, we're going to go ahead and find our Underwood expression for the stripping section. And like before, we're just going to get started by looking at our equilibrium curve. And this time, I'm going to examine our stripping line here. And we notice the same observation that as we're taking our steps up and we approach that pinch point, our compositions aren't really changing at the pinch point once we take so many steps up. So we can say the same thing as we said before, that yn equals kxn and yn plus 1 equals kx plus 1. And then, again, we know that these two values are roughly the same at the pinch point, meaning that xi equals yi. That'll be a useful substitution for soon. We're also going to look at the overall material balance for the stripping section this time. So as we've discussed, feels like 1,000 times before, we know that coming into our stripping section, we've got our L bar going out, we've got our V bar, and our bottom split D. Meaning that we know that L bar equals V bar plus E, and therefore putting in our compositions, we know that XI L bar equals YI V bar plus XI V times our bottoms flow. Then we're going to go ahead and sub in this substitution so we can get everything in the form of our YI here. So we can say that our YI over KI times our L bar equals YI V bar both of our yi's on the same page here, we get that yi times L bar over k minus v bar equals r xib times r bottoms of b. And then, of course, we isolate our yi here. We get that yi equals xib times b all over L bar over ki, specify that over here, minus v bar. And then really similar to what we did before with our rectifying section, we are going to multiply both of these by ki over kr. Which will give us yi equals we're also going to remember a very crucial part. Our alpha is always going to equal our ki over kr here. So that's our alpha IR. But we're just going to call it alpha for the remainder of this. Which means that we know that yi is now going to equal alpha xib times our bottom's flow b all over our L bar over kr minus v bar times alpha. And then again, similar to what we did before, we're going to factor out this v bar. And multiply it out over here. We're also going to factor out a -1 in order to put the negative on this other side to get our stripping section Underwood equation more into the form of our Underwood for our rectifying section so that we can combine them later, so in the last part of this derivation. But overall, by pulling out that v bar, factoring out the v bar and multiplying both sides by -1, what we're going to get is that negative v bar yi equals alpha xib times b over L bar over v bar times kr First, I've got our alpha here because we multiplied by -1. This is now positive minus our L bar over kr times v bar. And similar to what we did before, we're going to call this value just psi. So we're going to say psi equals L bar over kr times v bar. And once we sub that into there, we get that negative v bar yi equals alpha xib times b over alpha minus psi. And then, like we did previously, we're just going to take the summation of this, knowing that the sum of all of our yi's is just going to be 1, which means we get our final Underwood expression that negative v bar equals our bottom's flow times the sum of alpha xi b over alpha minus r psi. And that right there is the Underwood equation for the stripping section. And finally, what we're going to do is we're going to combine these two equations. Well, what I'm going to do real quick is erase all this because we're going to need a little bit more room for that derivation. Alright, get rid of all of this. Write this up here. So negative b bar equals b summation alpha xi b over alpha minus r psi. These are under stripping. And now we can move on to the combination of these two. And the first very important thing that Underwood did that we can't really derive on this board because it is a incredibly difficult thing to prove, but we can kind of hand wave it and just say that Underwood found out that our psi value equals our phi value, making it possible to combine these two equations into one really clean overall Underwood equation. And to get started doing that, we're just going to remember our overall material balance for the vapor phase of our entire column, which is that our feed times 1 minus q, and you recall that q is the liquid fraction of the feed, so 1 minus q is going to give us the vapor fraction of that feed, equals our v minus our v bar. And as you can see here, we've got these two expressions. We've got our v and we've got our minus v bar. So if we plug those two in right here, we get that our feed times 1 minus q equals our distillate flow times the summation of alpha xi d over alpha minus phi, plus, because we've got our minus v bar here, we're going to have our bottoms times our summation of our alpha times our xi b all over alpha minus phi this time, because of this equivalence that Underwood was able to find in his big giant paper. Very, very complex thing to derive there. So now we've got two like denominators here. We can combine a couple things here. So we obviously know that our distillate plus our bottoms flow, that's just our overall feed balance. So we can say that our feed times 1 minus q is going to equal our feed out here, as that's our d plus our b, so we can combine those into that, times the summation of our alpha. Now if we combine xid and xib, we're just going to get our z feed composition over our alpha minus our phi. And then again, as you can see, we've got our feed on both sides of this equation, so we can go ahead and eliminate that to give us our overall combined Underwood equation that 1 minus q equals the summation of alpha times our decomposition all over alpha minus our phi value. That right there is our overall Underwood equation. So now we derive that, we can go ahead and move on and do a little bit of an actual example of this in Python. So let's go ahead and move on to that section of the video. All right. After reviewing the problem statement for the last part of Part C, for the applying this into a Python example, I realized that we need to play around a little bit with the Underwood rectifying section equation here. So the form it's in right now does not include the reflux ratio, which we're looking to minimize in that last part. So I'm going to do a really simple walkthrough of how we can get the rectifying section Underwood equation into a form that makes it a little bit easier to apply to our problem here, just so that we have that derivation down and I don't just hand wave through that. Going into the Python part, so the first thing we're going to do is we're going to consider the condenser at the top of our tower. We know that coming up into our condenser from our overall tower, we've got our vapor flow V, we've got our distillate coming out, and we've got our reflux liquid L, and we know that the material balance around this is V equals L plus D. Pretty simple enough, but if we sub that in to our Underwood equation for the rectifying section, we get that L plus D equals D times the summation of alpha xi d over alpha minus phi. And then, of course, we're going to go ahead and divide over our D, which will give us L plus D over D equals the summation of alpha xi over alpha minus phi. And of course, to get this into the form of our reflux ratio, you need to remember that our reflux ratio R equals that L over D, that reflux liquid over our distillate. We can pretty simply see that if we sub that into this right-hand side, what we're going to get is that R plus 1 equals the summation of alpha xi d over alpha minus phi. And this is the form that we're going to use to later minimize this reflux ratio, as it actually has the value for the reflux ratio in it, but as you can see, it's pretty much just the Underwood equation we derived earlier with a little bit of a substitution in there for that reflux ratio. So now we are actually good to go ahead and move into our Python section. So I'll see you there.
Alrighty, now that we've went ahead and derived all of our Underwood equations up on the board, we're good to go ahead and move on to our actual example in Python here. We're going to determine the minimum reflux for an equimolar four-component feed with relative volatilities relative to the heavy key of 2.5, 2, 1, and 0.7 for each component, and a 50 mole percent liquid fraction feed, a recovery of 95% for the light key and 96% for the heavy key and the respective distillate and bottoms products. So to get started here, we're of course going to put in all of our provided values. So first thing we know is that our Q equals 0.5 as specified by that 50 mole percent liquid feed fraction. We also know that our light key recovery is going to equal 0.95, and then our heavy key recovery is going to equal 0.96, that 95 and 96% as we were talking about. And what else do we know? We know it's an equimolar four-component feed, which means that our Z values, our feed compositions, we're going to put those in as an array of 0.25s, 4 of them as like said in the problem, we got an equimolar feed, so each of these will each be 1/4 of the feed. Fantastic. And then we are going to put in our relative volatilities also into an array. So we're going to say that our alpha is going to equal NP dot array going from heaviest are 2.5 to 2 to 1 to 0.7. And I think that that is all we know from the problem. So moving on from there, I need to go ahead and run my CHE tools as well. Sorry about that. We ran into some issues because I forgot to run that our CHE tools up here, but now that it has run, we're able to use those np.arrays. What we're also going to need to do is we're going to need to specify our feed, which we're just going to call 1, as that is not really specified in the actual problem up above. So we're safe to just say it is 1 and go off of our z values. We also need a light key index and a heavy key index. So our heavy key index is going to equal 2. And that, of course, is because our 1, that's our 2 relative volatility value. So the more volatile component nearest to each other, that's our light key and our heavy key, and then our 2 is, of course, that 1 value. So now we have those indexes for the alphas that correspond to our light key and our heavy key. We can go ahead and calculate the distillate weight. So the combination of everything coming out, the weight of the stuff coming out of the distillate. So we're going to call that our WD. And our WD is going to equal our feed times np dot r underscore, and the first, I need to put a bracket there. Our first part of this this concatenated array is going to be our z at everything above our light key, because everything lighter than the light key, that's all going to go up into the distillate, and not all of the light key is going to go into the distillate. A little bit is going to be found at the bottom, but anything lighter than that light key is going to be going straight into the distillate. So we know that we don't need to subtract anything out. We can just say that it's all going to be going up into the distillate flow. So we can say z at our light key index. Need to move that comma because it's everything above our light key index for that first value. And our next one is going to be our light key recovery times our z at our light key index. And then, of course, we've got 1 minus our heavy key recovery times our z at our heavy key index. And then for the final one, we know that anything below our heavy key is going to be found in the bottoms. There's going to be none of that stuff in the bottom in our distillate flow. So we can say that z at hk index plus 1. We're going to multiply that by 0, as none of that is going to end up making it up into our distillate flow. So I believe that's our entire index to find our weight of our distillate. But to find our composition, our XD, we're just going to take our WD over the sum of all of our WD values. I think that's all good. Yep, seems to work out. So now we need to define our Underwood function. And we know this is a function of that phi value we were talking about earlier. And then from there, we're just going to return that Underwood function, but we're going to move the 1 minus q to the other side of the function because we're going to be doing like a minimization. So we want that one side to be at 0. So we're going to return, we look up at the board here for our function. Return mp.sum of alpha times our z value divided by our alpha minus our phi value. We're going to subtract all that 1 minus our q, which gives us our Underwood function. So we can shift enter there. And I think that we can go ahead and create our phi graph after we vectorize this Underwood function as we're having several different values here. So we're going to say that Underwood vec is going to equal jnp dot vectorize of our Underwood function above with the following signature. That's going to be our parentheses. Perfect. So now you've got that vectorized Underwood function. We're getting good to go ahead and graph where those phi values are compared to each other. So we can say fig equals make subplots. Then we're going to do fig dot add scatter. We're going to have our, well, first, before I do this, I need to create our phi's at all. We need those to exist. So to create our phi's, say that our phi's are going to equal an mp dot line space going from, we're going to go from 0.9 times the minimum value of alpha. That way we're getting just a little below the very lowest point of our alpha value so that we're going to be able to cover this whole spread, to 1.1 times the maximum of alpha. Again, so that we're getting a little below the minimum of that alpha and a little above the maximum of that alpha. And then we'll want 1,000 points in between. So now we can go ahead and move down to our fig.addScatter. And we can say that our x values are going to equal our phi's, our y values are going to equal our Underwood vectorized function of our phi's. And of course, we're going to do our mode equals lines. I think that should be all good. We also want to update our y-axis. I forgot this is an asymptotic function. Once we hit our alphas in our function up here where the denominator goes to 0, we're going to have this crazy asymptotic function. So we're going to make this entire graph look pretty much unreadable unless we go ahead and update that y-axis to limit it down to just like -3 to 3, so we know what we're looking at. So I'm going to go ahead and update y-axis going from -3 to 3. Hold on. Oh, I forgot to put our range equals -3 to 3. Shift enter. Beautiful. So what we're looking at here is you can see when our alpha values, when our phi's equal our alpha values, the denominator of this equation up here is going to 0, which is causing these crazy asymptotes. And then this is our phi, where we're crossing the x-axis here. Our actual phi values are our roots. And what we're gonna want to look for, so we have one for our heavy key and one for our light key here. We want the one that is in between, which is right here, which is going to be about 1.38 when it comes to minimizing our reflux ratio R. We want that middle phi value there. So just to get that, I guess, in writing, so I'm not just putting in a guess, we're going to use the SciPy root scalar function on our Underwood equation to find where exactly that phi value is. So we're going to call phi root equals SciPy optimize underscore root scalar of our Underwood vectorize, and our initial guess, as we said, we're looking for the value that's right around in the middle there. So we're going to have our x naught equal 1.5. Then let's spit out that value. Perfect. That looks all good. That is our phi value that's right here that we're going to now use with our other equation we figured out up on the board to find our minimum reflux ratio, which we'll call R min right now. And that R min is going to equal our function up here that we calculated up here, but solved for R. So we're going to subtract out that 1. So we're going to say it's the np.sum of our alpha times our xd. That, again, is the form of our Underwood function for the rectifying section, normalized to the reflux ratio that we just calculated up on the board. I'm going to put this in another set of parentheses. Divided by, we're going to do our alpha minus our phi root that we just calculated up above, and we're going to subtract this entire thing by 1, as up on the board we calculated the left hand side to be R plus 1, so we're going to subtract out 1 to get our R value minimized. So let's see what it spits out here. Hold on 1 minute. I see I forgot to put a dot root up here, so it was spitting out a root result, this whole thing right here, instead of just the float value. So I correct that. That looks just about right. So our minimum reflux ratio given these above conditions is going to be about 1.66. I think that is the end of this segment of homework 3, the end of part C. So I will see you in the next one.